Hey guys, Ms. Peterson here, and welcome to our chemistry lecture on solutions and concentration. In this lecture, we're going to be going over some of the vocabulary for how we describe solutions and how we quantitatively calculate and express concentration using molarity. Let's get started. So, what even is a solution? Okay. Well, in chemistry, most of the time, we do our experiments in water, an aqueous environment. So when we have chemicals that are dissolved in water or something else, we call it a solution. Now, there are two parts of the solution. There is the solute and the solvent. Okay, the solute is the thing that you dissolve into it. Typically the solid that you mix in, or it could be a gas in the case of like soda with the carbon dioxide bubbles dissolved in it. And the solvent is the main species present. Now, the universal solvent is water. Water is going to be your solvent 99% of the time. Okay, cool? Okay, cool. Now, let's look at some examples, okay? We can look at lemonade as an example. Water is the solvent, and the lemon juice and the sugar are going to be the solutes. What about this air all around here? Anybody know what the solvent in air is? It's actually nitrogen. Air is 78% nitrogen. The solutes are, the main one is oxygen at 21%. And then we have carbon dioxide and hydrogen gas and maybe some sulfide compounds are in the air. Okay. We'll also talk about solutions in the context of chemistry, where we'll say something like 2.0 molar HCl, which is 0.2 molar hydrochloric acid. That means that water is the solvent, and then the hydrochloric acid is going to be the solute that is in that water. Okay? So, how do things dissolve? It's important to remember that not everything dissolves the same. Okay? When something dissolves in water, it's not that it disappears. Yeah, we can't see it anymore, but that's just because the water has broken apart the particles into really small particles. That happens due to attractions between the water and the solute. So for covalent compounds like sugar, they'll dissolve into individual molecules. So in your soda can, okay, you got water as that solvent, and you have individual molecules of carbon dioxide gas that group together and form the bubbles. You have the individual molecules of sugar and all of the flavor-containing compounds, which some of those might be ionic compounds. Now, when ionic compounds dissolve in water, they will typically break apart into individual ions. So if I dissolve some calcium chloride in water, there's not really any calcium chloride bonded together in that structure anymore. Rather, we'll have calcium ions and chloride ions floating around in the water. Specifically, for every mole of calcium chloride we dissolve, we'll get 1 mole of calcium ions and 2 moles of chlorine ions in that solution. Now, like I said, this is due to attractions between the water and the solute, and that leads to something that we call like dissolves like, meaning that a polar solvent, like water, water is polar, will dissolve a polar solute or an ionic solute, where non-polar solutes will not dissolve, okay? Oil is a big non-polar molecule. It doesn't mix with the water because there's not that attraction there. Okay, cool? Okay, cool. So, how do we describe solutions? Well, qualitatively, we can describe solutions either more concentrated, meaning there's more solute in there, or more dilute, there's more solvent, there's less of that solute. And then we also have the word saturated, okay? Now, if you have a rag that is saturated with water, it's not going to absorb any more water. If you have a solution that is saturated with solute, it will not dissolve any more solute. So it has the maximum dissolved. Okay? Now, if we want to talk about these quantitatively, so using numbers, we use molarity, where molarity is the moles of a substance per liter of a solution. So you can kind of look at that as an equation where the molarity, capital N, is N, the number of moles, divided by V, the volume of the solution. Okay? You can also kind of think of it like a conversion factor. So a 2 molar solution of sodium hydroxide, NaOH, contains 2 moles per liter of water. So its units, forgot to write the units. The units of molarity are moles per liter. Okay? So we can use it like a conversion factor, or we can use it in that equation form. Let's go ahead and see some examples of how we do that. So if I dissolve 3.5 moles of water into 2 liters of water, what is the molarity? Well, we're looking for the molarity. We know the moles and we know the liters. So molarity is just the moles per liter. Okay? The units tell me how to solve it. We have the 3.5 moles divided by the 2.0 liters. Okay? So we just plug it into our calculator, 3.5 moles divided by 2.0 liters, and we get that it is a 1.75 molar solution, okay? Which you can write as capital M, but it's also totally fine to just write it as moles per liter. Okay, cool. Let's look at a slightly harder one. If I need 0.5 moles of HCl, then how many liters of a 6-liter solution do I need? What if I want that in milliliters? Okay, we're going to go ahead and solve this using dimensional analysis. So I need 0.5 moles. I want to know how many liters of a 6-liter solution I would need if I only need the 0.5 moles of HCl. Oops, sorry, this should say point of a 6 molar solution. Okay, capital M there, not liters, sorry. Yep. So we're going to start with our known, the 0.5 moles of HCl, and then we can use this 6 molar like a conversion factor. It tells us that there's 6 moles in 1 liter. So if I need 0.5 moles, well, if there's 6 moles per liter, I would do 0.5 divided by 6. And I would get 0.083 liters. Now, that might be a little weird to measure out on a graduated cylinder or something like that. So rather, let's go ahead and put it in liters. And we can actually do that by adding one more conversion factor onto our problem. So this would give me the answer in liters, but I know that 1 liter is 1,000 milliliters. So the mole units cancel out and the liter units cancel out, and I have that 0.083, 0.5 divided by 6 times 1,000, which gives us 83.3, so we'll just go with 83 milliliters, which would be much easier to measure out on our scale. Okay, cool? Okay, cool. Or on a graduated cylinder. We wouldn't measure milliliters on a scale. Let's go ahead and look at one more, because we do often measure our chemicals on a scale. So how many grams would I need to weigh out to make a 1.5 molar solution of NaOH? And let's say I want to make 2 liters of it, of that 1.5 molar solution. Okay. Well, anytime you see grams in a problem, what do you know you're going to need? Molar mass, okay? Anytime we're dealing with grams, we're going to need that molar mass. So I'm going to calculate the molar mass of NaOH. Okay? We have 1 Na, 1 oxygen, 1 hydrogen. We go to our periodic table to find the values. Sodium has a mass of 22.99. Oxygen 16.00, and hydrogen 1.01. So since it's just one of each of those, we can just add it up together. And we get 40. 40.0 grams per mole is the molar mass of NaOH. Okay? So now let's go ahead and set up our problem. Our known is going to be the 2 liters. That's how much we want. And then we can use this 1.5 moles per liter as one of our conversion factors. Same with the molar mass. So I'll go ahead and change colors here for it to make it clearer. We'll start with that 2 liters. And then I know that in each 1 liter, there are 1.5 moles. So that would tell me, if I solved it out, 2 times 1.5, the number of moles of NaOH I need. But I want to know grams. So how do I convert from moles to grams. Molar mass. So I know that 1 mole of NaOH has a mass of 40.0 grams. So that can cancel out the mole units, and now I have 2 times 1.5 times 40, which gives us 120 grams of the NaOH. I would dissolve that in the 2 liters of water and have my 1.5 molar solution. Okay, cool? Okay, cool. Now, one last other thing I wanted to talk to you guys about, and that's some of the other ways that we express concentration. Okay? We'll use percent by mass or volume. That's what you'll see the most on like cleaning products, or often used in like manufacturing things. You can see it on this little bag of calcium carbonate, that it's 94 plus % pure. Okay, so that works. You can see it on vinegar, that it's diluted to 5% acidity. And then another important one that you see a lot is in graphs like this of our atmospheric CO2. The y-axis here is in parts per million. So ppm, parts per million, and ppb, parts per billion, are often used in like atmospheric and oceanic chemistry, whenever we have really small concentrations that actually make a big difference. So, for example, the atmosphere is 221 parts per million carbon dioxide, meaning if you took 1 million particles that are in the air, 221 of them would be carbon dioxide. Okay? And that's what you need to know about solutions and concentration. Okay, cool? Okay, cool.